Today, I'm going to be discussing simple gas laws used in General Chemistry 1 and onwards by Melissa Basily. It is worth acknowledging that Principles of Chemistry and Molecular Approach with Mastering Chemistry by Navaldo Tro was used as a source for the following formulas. First, it's important to understand the purpose of these simple gas laws, which is to understand and predict the behavior of gas properties such as pressure, volume, and temperature. Starting with Boyle's law. Boyle's law is the following. Initial pressure times initial volume equals final pressure times final volume. Boyle here indicates an inverse relationship, meaning that as one property or variable increases, the other should decrease, and vice versa. In this case, if pressure were to increase, volume is expected to decrease. This formula is true at constant temperature and constant particle amount. How can this be applied? To the right is an example. A 2-liter balloon is at 1 atmospheric pressure. If its volume is reduced to 0.5 liters, what is the new pressure? The key to solving something like this is first identifying what is given and what is needed. We are given the initial pressure, the initial volume, and the final volume, but we need the final pressure, which is not given. And so we write the equation. Then we substitute the knowns and the unknowns accordingly. And finally, we isolate the unknown. Before calculating the answer, we expect for the final pressure to be greater than the initial pressure since volume was decreased. This goes back to the inverse relationship that Boyle's law indicates. And it's true. The final pressure is greater than the initial pressure because the volume was reduced. Charles' law indicates a direct relationship in comparison to Boyle's law. Here he claims the initial volume over initial temperature is equal to final volume over final temperature, which are indicated by V1 over T1 equals V2 over T2. Again, pressure and particle amount need to be constant for this law to be applied. Here, Charles indicates that as one variable increases, the other should also increase with it. So if volume were to increase, temperature is to increase as well, which goes back to predicting behavior. So, to the right is an example. A gas has a volume of 3 liters at 300 kelvins. If it is heated to 450 kelvins, what is the new volume? Assume pressure is constant. Again, it's important that pressure and particle amount are constant for this law to be applied. Now, which is assumed if not stated like in this question. Okay, so like in the previous example, we can predict the answer or ensure its accuracy by looking at the type of relationship between both properties, volume and temperature, because Charles' law claims that volume and temperature have a direct relationship. An increase in one should lead to an increase in the other. Because the temperature is increased via the heating, then we expect the volume to increase more than 3 liters, the initial volume. So, as in the previous example, we write the equation, we substitute what is known, which is given in the problem, isolate the unknown, and reach our final volume, which is, as expected, more than the initial volume, because with the increase in temperature, we predicted that the volume would also increase. Now, Avogadro's law. Sorry, I don't know why that's written twice. Avogadro's law also indicates a direct relationship like Charles' law. Now, he claims that initial volume over initial particle amount, or moles, is equal to final volume over final particle amount, or moles. Now, this claims that as one increases, the other should also increase. So if volume were to increase, the particle amount should also increase. Again, this goes back to the direct relationship. And it's important that pressure and temperature are constant for this, which is implied unless otherwise indicated. To the right is an example. A gas occupies 5 liters at 2 moles. How much volume would 3 moles of the same gas occupy at the same temperature and pressure? Now, because the amount of particles or moles was increased due to the direct relationship indicated by Avogadro's law, we also expect the volume to increase. So again, the first step is to write the equation, then substitute what is known, which is the 5 liters over the 2 moles is equal to the unknown volume that we're solving for over its 3 moles. Isolate the unknown, which is by moving the 3 over, and finally we reach our final volume, which is, as expected, greater than the initial volume of 5 liters. This is because the number of particles or moles has increased. My apologies again. Ideal gas law. This ideal gas law is the most common of the 3, and it is used very often. It is used to find an unknown property. In the ideal gas law, pressure times volume is equal to moles, or N, times the gas constant, R, times temperature. How can this be used? Well, an example is in the right. It is used to find an unknown property when, let's say, all others are known. So a sample of gas has 1.5 moles at 2 atmospheric pressure and 300 kelvins. What is the volume of the gas? But wait, we are not given R. What is R? We will get to that in a second. The first step is to write an equation depending on what we have. So because we have 3 variables, we know that we're going to need to use the ideal gas law instead of, let's say, Boyle's law. So after writing the equation, we substitute what we know, which is the 2 atmospheric pressure times the volume, which we're solving for, is equal to the 1.5 moles times a gas constant, 0.0821, which depends on the units of pressure and volume. Because our unit of pressure is ATM and the unit of volume is in liters, we use the constant 0.0821. There will be other situations where the gas constant will be changed if the units of pressure and volume are not in ATM or liters, which I will get to. And then we have the 300 kelvins. So again, we isolate the unknown and finally reach our final volume of 18.5. This table shows another R value that is also commonly used, and that is when our units are in joules, which differs from the units of liters and atmospheric pressure used here. In that case, the R value would be 8.314. And that is all for simple gas laws.